Hey everybody, thanks for tuning in to our second video on differentials. Our first video dealt with a certain type of differential. We were using it to estimate square roots and cube roots of numbers that normally we wouldn't be able to find without a calculator. Today we're going to switch it up. We're going to use the same formula that we established on the last video, but we're going to use it in a slightly different context. So let's take a look at example 1. It says, a spherical bearing, which I didn't know what a spherical bearing was, but this is what it is right here. I snipped this offline. A spherical bearing has a radius of 3 centimeters when it is new. Use differentials to approximate the volume of the metal lost after the bearing wears down to a radius of 2.971 centimeters. Okay, well, it says to use differentials. So as soon as I see that word, it triggers in my memory the formula that we derived yesterday. So I'm going to start with that formula right here. So the formula says that f of x plus the differential dx is approximately f of x plus dy, right? That was the original formula. Then we wrote dy in terms of x. So then the formula became f of x plus dx is approximately f of x plus f prime of x dx. So we learned that dy and f prime of x dx mean the same thing. And if you have forgotten why that is, you can look back at your notes from yesterday. Okay, now in this problem, we're talking about volume and radius. So watch what I'm going to do to my formula. I'm going to change it and write it as, I'm going to change it and I'm going to change colors. I'm going to do volume instead of F. The volume of radius plus a change in radius will be approximately volume at a certain radius plus v prime at that radius times dr. And so if this guy right here was equivalent to dy, change in y, then I'm thinking that this guy right here, this part of the formula, this second half, is going to represent a change in volume, dv. Okay, so let's start plugging some things in. Let's talk about our radius. Well, the radius started at 3 centimeters, radius of 3 centimeters. And this is before it wore down to a smaller radius. So I'm going to let the r's in this formula be 3. So it'll look like this. Volume of 3 plus, now I'm going to leave a space for dr, is approximately v of 3 plus v prime of 3, and I'm going to leave a little space there to multiply by my dr. So what's dr? Well, change in radius. Well, if we wore down to this radius, then the change in radius is going to be, and you could do this in your head too, but 3 minus, can you see that there? 3 minus 2.971 is 0.029. 0.029. So my change in radius went down. Now I'm going to make that negative because it decreased by 0.029. So back here I'm going to multiply by negative 0.029 as my dr. Okay, so what does this give me? Well, now I have volume of, if I take 3 plus negative 0.029, I get 2.971. So this is going to give me my approximate volume when the radius is 2.971. So now I have to find the volume when the radius is 3. So let me come off to the side here. So the volume of a sphere is 4/3 pi r cubed. So my radius at 3, I would put a 3 in there. And if I evaluate that on my calculator, I get 4/3 pi times 3 to the third. I get 113.097. I'm going to go ahead and store that in alpha A so that I have it unrounded. So 113 0.097 plus. Now I need v prime of 3. Well, v prime is going to be, well, what's the derivative of 4/3 pi r cubed? Think about that. I'll write it down here. 4/3 pi r cubed. Well, if you use the power rule, 3 times 4/3 is 4 pi r squared. So you're going to reduce the r by 1, the exponent on the r by 1. So if I put a 3 in there, this would be v prime of 3. So this is going to be 4 pi times 3 squared. And look, it's the same thing. It's 113.097. So 113.097 times negative 0.029. Okay, keep going. I'm going to bring down my 113.097, and now I'm going to multiply these two. So if I take 113.097 unrounded times negative 0.029, I get negative 3.2, I'm going to say 8. Negative 3, I'm going to store that. Where am I going to store that? Store that in B. Negative 3.28. And finally, if I add these two together, so I'll do my alpha A plus my alpha B, I get 109.818. 109.818. 109.818 centimeters cubed. Now, let's dissect this for a second. Okay, here's what we've got. We did all this, but do we know what it means? That's the important thing. Okay, let's talk about the 113.097. This is the actual volume of a sphere when the radius is exactly 3. This is this calculation, okay? This calculation right here is the approximate volume of a sphere when the radius is 2.971. I say approximate because it's as per the tangent line drawn at 3. Okay? So now, what is this? Well, this guy here on the back is my change in volume. It's the error in volume that occurs when you change your radius from 3 to 2.971. In other words, if I take this minus this, I get this. So this is my change in volume. So why am I bringing all this up? Well, look at the wording of the problem. You would think that this down here is your final answer, but it's not. It says, use differentials to approximate the volume of the metal lost. Well, the volume of the metal lost between here and here is this guy right here. So that's how we have to answer this problem. So I would say, when the bearing wears down to a radius of 2.971 centimeters, the volume of metal lost is, ready? And I don't have to put the negative because I used the word lost, is 3.28 cubic centimeters. So you kind of have to dig in here to find this. Now, in a picture, guys, check this out. So think about our notes from yesterday. If you're visual, right? Instead of having f of x and x, we have volume and radius. And so we know the volume when r is 3, right? I'm just going to draw. I don't know that this is really what the curve looks like. I'm just going to try to use the drawing from yesterday. So this is like the P from yesterday. So when r is 3, we know the exact volume is 113.097. So 113.097. Now, we're getting the approximate volume at 2.971, which is a little less than 3, because we drew the tangent line at P, and we are having a change in R, a dr, which results in a change in volume, dV, as per the tangent line, and that dV is this calculation right here. So we're approximating that our volume lost is 3.28, which puts our tangent line Y value at 109.818. But the true, now that's an approximation because we're using the differential and the tangent line. The true volume lost is actually a little less than that. Do you see how the tangent line lies underneath here? What I'm saying is, if we know the volume, let's calculate the actual volume at 2.971. If you do 4/3 pi times 2.971 cubed, let's see what we get. You would get 4/3 pi times 2.971 to the third. See, 109.849 cubic centimeters. See how that 109.849 is bigger than 109.818. Not much, but you can see the actual loss of metal is a little bit less than the approximated. But it's so close. That's why we like to use differentials, because we can use the tangent line to approximate more difficult curves. Okay, last one. Very similar. Example 2. The radius of a sphere is measured to be 7 centimeters with a possible error. Here's my dr, my change in radius, of plus or minus 1/10 of a centimeter. Estimate the possible propagated error in the calculated volume. Okay, I'm going to go right to this guy. Since we're dealing with volume and radius again. So volume of R plus dr is approximately V of R plus V prime of R times dr. So what's my radius? Well, my radius is 7. My R is going to be 7 centimeters. So V of 7 plus, leave a little space, is approximately V of 7 plus V prime of 7 times, leave space. So what's my change in radius? Well, my error is plus or minus 1/10 of a centimeter. So for the purposes of writing this example, I'm going to start with, let's just say it's positive 1/10. Let's just make this 1/10. Then this becomes 1/10 back here, okay? So if we're trying to find the volume, approximate volume, if your radius changes by 1/10 of a centimeter, then we have to calculate this side over here. So V of 7, again, it's a sphere. So the volume of a sphere is 4/3 pi r cubed. 4/3 pi r cubed, so 4/3 pi times 7 cubed is 1436.755. 1436.755. I'm going to store that in A. Store that in A. Okay. Now, plus. Well, the derivative of 4/3 pi r cubed is V prime equals 4 pi r squared. And again, if you're confused as to where I'm getting all this, what I'm doing is I'm taking 4/3 pi r cubed. When I take the derivative by the power rule, 3 times 4/3 is 4 pi r, and you reduce that by 1. So 4 pi r squared. That's where I'm getting 4 pi radius squared. So if I put that into the calculator, 4 times pi times radius squared, I get 615.752. 615.752 times 1/10. All right, let's keep going. V of 7 and 1/10 is approximately 1436.755. Multiplying this decimal by 1/10 is just going to move the decimal one spot to the left, so 61.575. And when I put this all together, my approximated volume when we increase the radius by 1/10 of a centimeter is going to be what I had here in, oh, you know what I should do here? Let's do this. Let's multiply this last answer times 0.01. No, not 0.01. I went too far. Hold up. Clear this out. 4 pi times 7 squared. I should have stored that in B. Now, multiply that by 0.1. There we go. I'll store that in C. Okay, so I have to basically add A to C now. So alpha A plus alpha C. Okay, 1498.33. That's this calculation. 1498.33 cubic centimeters. Now let's interpret. You ready? This is the volume at 7. Volume of a sphere with a radius of 7. We increase the radius, which creates a change in volume. This is my dV. And when I change by that much in my volume, my new volume is estimated to be higher than what it was, which makes sense. If you increase the radius from 7 to 7.1, the volume should increase. Okay? But by how much? Well, it says estimate the possible error in the calculated volume. This is the error right here because these two differ by that much. So when the radius of the sphere is off by plus or minus 1/10 of a centimeter, the volume will be off by plus or minus, here it is, 61.575 cubic centimeters. Now, why do I say plus or minus? I didn't do the minus. Well, let me address that. If this had been negative 1/10, this back here would have been negative 1/10, and we would have been finding the volume when the radius is 6 9/10. But all that would have done, it would not have affected this calculation. It would not have affected this calculation. It would have affected this right here. This would have changed to a negative, and this right here would have been less than our original volume at a radius of 7. So that's why I can simply put the plus or minus in the plus or minus, because whether this is plus or minus 1/10, this just gets affected by either plus or minus 61.575 cubic centimeters. So that, feel free to just put those plus or minuses on. Okay, your mastery is 6 problems like this, so good luck with that, and thanks for watching.